So I think we can get started. And so the thing that we learned last time was that one of the pillars of general relativity is the principle of equivalence. So we built the fundamental equations that we were able to write down last time, which was the equation for free fall, out of this fundamental principle, which I will repeat again, asserts that in an arbitrary gravitational field, right, you can find a special coordinate system, which is a so-called freely falling coordinate system, in which the laws of special relativity apply. So in that coordinate system, right, which we denoted by, so we have a general coordinate system, right, and then we have this coordinate system labeled by xi alpha, which is inertial. The point of the equivalence principle is that you can always find such a coordinate system, the freely falling one, where gravity is absent. That is, there is no acceleration, and you have the laws of, well, unaccelerated frames, which, to be more precise, are the laws of special relativity, right? That's why we use the indices alpha, beta, gamma for the coordinate system of special relativity, and index mu for any other sort of general coordinate system. So in this inertial coordinate system, we have that the second derivative of xi alpha with respect to tau squared is equal to 0, right? And then what we do is we transform back, right, from the xi alpha. We transform to this coordinates x mu, right? And we bring in things that are of the form dx mu by dxi alpha, right? These derivatives. So by manipulating derivatives, we write down the equation of free fall, right? And is that the second derivative of, let's write it as second derivative of x lambda with respect to tau squared plus gamma lambda mu nu dx mu dx nu by d tau is equal to 0, right? And so that's the equation for free fall. Equation for free fall, or also called sometimes the geodesic equation. Right. And so at this stage, it's not clear that this equation really is necessarily useful, because we just obtained it by transforming from one coordinate system to another. And the gamma, the affine connection, is given by some derivatives of one set of coordinates with respect to another set of coordinates, right? And so the other thing that we mention is that if you look at the proper time interval, this, well, in the freely falling frame is given by this metric eta alpha beta dxi alpha dxi beta. So this is equal to minus eta alpha beta dxi alpha dxi beta, right? But in a general frame, it is minus g mu nu, which will depend on x, times dx nu, right? So there is a relationship between the proper time and the metric, and the metric is related by this change of coordinates from the xi to the x, right, as we discussed last time. Now, the other crucial ingredient that we derived in the previous lecture was the fact that you can write the gamma lambda mu nu as a function of g mu nu only. That is, a function that does not involve the xi alphas at all, right? And so that was the result we obtained last time, and that is that gamma sigma mu nu, right? Gamma sigma mu nu is equal to 1/2 g sigma, and then times lambda, or let me write this as lambda. Let me keep the indices the way I have them here. gamma lambda mu g sigma nu times 1/2 times some set of appropriate derivatives of the metric, which are, first of all, dg mu nu by dx lambda, and then the derivative of g lambda nu by dx mu, and then the third derivative, which is the derivative of g mu lambda, derivative with respect to dx nu, dx sigma, sorry. Dx nu, like this. So that means that the gamma lambda mu nu is determined, well, I already wrote it up there, so it's completely determined by the metric. So if we know the metric, then we can calculate the affine connection. And so if we know the g mu nu, then we know the gamma lambda mu nu. And if we know the gamma lambda mu nu, then we know the equation of free fall. We know this equation of free fall, so that means that we can now go and put that in there and solve this equation, right? So again, the issue is whether this is of any use, right? Because do we learn anything new that we didn't learn, that we didn't know before? And by the way, this also required the introduction of a inverse of the metric. Right? So what we would denote as g to the minus 1. In this case, it has the indices upstairs. So we have a g mu sigma, g sigma nu is equal to delta mu nu. So this is the metric, and this is the inverse of the metric. Right? And if the coordinate systems are well behaved, then all the derivatives of one coordinate system with respect to another, for example, derivative of xi with respect to x, coordinates are finite and well behaved, then this inverse exists. And so that is something that we need to know, because the inverse of the metric appears in there. Right? So you wonder how you're going to remember these indices and the way they're placed. Well, let me show you that there is a certain pattern, right? There is a certain pattern because, for example, if you take these two indices, lambda mu, which I'm going to write in blue, lambda mu, right? Then we have here the lambda, and here the mu, and here again the lambda, and here again the mu, right? And then we have the lambda and mu. Remember, the metric is symmetric, so you can order the indices any way you want. So you can see that these two indices appear in certain combinations which are very similar for the first two terms, and that's why the first two terms have a plus. And in the last term, the bottom two indices in the gamma appear both in the metric, and that has a minus sign. So there is a little bit of a pattern there, right? And so this is something that one can remember, and is some peculiarity of the definition of the affine connection, that it has that sequence of derivatives, and well, that is the way it is. All right, so now, as I said, in order to see whether this equation can do any sort of useful work, we should try to see what it looks like for a system that we are familiar with. Right? And a system that we are familiar with is a particle, right, that is in a gravitational field. And we take that gravitational field, for example, to be weak, and see what we get. So we're going to do that in a second. But before we do that, let me erase this because I need the space. Let's derive another very interesting and fundamental result, and that is the the form of the geodesic that arises out of a variational principle. So this variational principle is quite interesting, namely the statement, right, is that you will get a geodesic if you do the following. You consider the proper time interval, right, and that is for a path, right, which is going to go from point A to point B, and which will have some proper time associated with it. And so we are going to do this integral from A to B, and this is going to be our TAB, our total elapsed time along this path. And now we are going to do a variation of that, variation from A to B in d tau, and set that equal to 0. Right, so this is the kind of variation that we do in classical mechanics when you look at the least action principle or Maupertuis principle. So that means that you have one trajectory here, which is x mu of some time, and you consider a neighboring path. So the neighboring path would be x mu of tau plus delta x mu of tau. Right, so you consider one path and a neighboring path, and now you do this variation. All right. So in order to do this variation, there's a little bit of mathematics involved, and again, as I said, we are going to do some of these calculations initially in an explicit way, and then later on, I think we will do less of them because they tend to kind of repeat themselves. And so let us do this variation. So the variation of the integral from A to B in d tau, which is equal to 0. Right? Well, the first thing we're going to do is we're going to parameterize this path in terms of some parameter. So P is some parameter which belongs, say, to the interval between 0 and 1, right? So this is P equal to 0 here and P equal to 1 there. So we introduce a parameter that labels the point along the path, and that parameter is just some real variable. So now we bring in the metric, and so we do that by writing the d tau, right? I can write it here again. Remember that d tau squared is equal to minus g mu nu dx mu dx nu. Right? So the d tau itself is the square root. Right? So the tau itself is going to be, right? And let me still have the variation symbol here in front. So it's the variation of the square root, right, of minus g mu nu, and then dx mu by dp and dx nu by dp, right? So now when we do the variation, right, we carry the variation symbol inside the integral, and we just vary the square root. And the first thing we do is, of course, the first thing we get out of that variation is a factor of 1/2, because we have the square root, the inverse of the square root itself, and then the variation of what is inside this thing, right? So this is equal to 1/2 times the integral from a to b in dp of 1 over the square root, right, minus g mu nu dx mu dx nu by dp by dp, right, square root, and then the variation of what is inside the square root itself. All right. So the variation of what is in the square root is minus so the first thing we vary is the metric itself. So we're going to get minus the derivative of the metric with respect to a coordinate. So we're going to call that with respect to dx lambda, right? And then times the variation dx lambda. Right? So that's the first thing. Times, of course, these two terms, which we just carry over. So times dx mu by dp and dx nu by dp. Right. So that's the variation of the g mu nu, right? And then we have a second term, which is the variation of the dx mu by dp or dx nu by dt. Now, the variation of these two objects is going to be the same because they have the same structure, and in fact the metric is also symmetric in mu and nu. So instead of having a variation of each one, we have twice the same type of variation, right? So we get minus 2 g mu nu, right? And then times the variation of dx mu by d tau, and then times dx nu by d tau, and then close parenthesis. Right. And now what we can do here is that the variation in the variation of dx mu by d tau is the same as d by d tau of, we don't need a parenthesis, of the variation of dx mu. Right? And the reason for that is the derivative is a linear operator, right? So the variation and the derivative with respect to tau commute, right? You can do them in any order, right? So that means that we are going to have d by d tau of dx mu in here, and then times that. Right? And so what do we do at this stage? Well, we do what you usually do already in classical mechanics, where we do the variation with respect to q and q dot. Right? You do remember that you vary with respect to q and you vary with respect to q dot. And this you can write as d by dt times the variation in q. Exactly by the same argument we have there, we can interchange the derivative with the variation, right? And so in classical mechanics, after we have done this, this manipulation, we then integrate by parts. You remember that? Right? So this is by parts. Integrate by parts, this derivative, which means that we're going to rewrite the derivative as something that acts on the rest of this expression, which is the g mu nu, and this other derivative here, right? Now, when we integrate by parts, we have to keep in mind another thing, namely that the variation of the path is 0 at the two endpoints, which means that we just get another integral and no boundary terms. The boundary terms is 0 because the variation is 0 at the endpoints, right? Right, so the variation is 0 here, right? It's 0 here, and of course it's 0 at the other point, right? Now the other thing we're going to do is actually get rid of all the dp's, right? Because we are going to just use everywhere that dp is equal to dp by d tau times d tau, right? And when you do that, all the dp's actually go away, and you can rewrite this just in terms, again, of the proper time. So we're going to do that. Remember, differentials can be just manipulated as if they're fractions. So dTAB, which is, of course, equal to 0, right? So we're going to rewrite it as an integer in d tau from a to b. Right? And so the first term we have is so when we change from p, we pick up this dp by d tau, and that is just the square root. So the square root goes away, and we just have minus. So the first term, Well, the first term, we're just going to leave it as it is. So I'm just going to copy this term over, right? Except we'll have the d tau. So minus g mu nu times, the derivatives, minus the derivative of g mu nu by dx lambda, right, times the variation dx lambda, and then times dx mu by d tau and dx nu by d tau. So that is just this first term where we have eliminated the p and replaced it by the tau. So the next term is minus g mu nu times the derivative with respect to tau of dx mu, and then times dx nu by d tau, and then close parenthesis, right? So as advertised, this is going to be done by parts. By parts. Right? So let's see what we get when we integrate by parts. So minus 2, there's a factor of 2 here, minus 2 g mu nu times d of the variation of x mu by d tau times dx nu by d tau is equal, right? Or I should say equal because it's inside an integral, so this by parts. Right? So this is going to be equal. Well, we are going to have two terms. One where the derivative acts on g mu nu, and another one where the derivative acts on dx nu by d tau. Right? So, and of course a reversal of sign as well. Reversal of sign because we integrate by parts. So 2 times. So we get the derivative of g mu nu with respect to tau, and that we can write as the derivative of g mu nu with respect to the coordinate x sigma, and then the derivative of x sigma with respect to tau. Right? So that's one term that takes the derivative of that. And then, of course, we're still left over with dx nu by d tau, which we just carry over, right? And then times this variation, all right? So times that variation, which we're going to write over on this side as dx mu. We're going to factor that out, right? And so the other term that you get when you integrate by parts is not the derivative of this one, but is the derivative of that with respect to tau. Well, the derivative of this with respect to tau just gives a second derivative. So that is easy, and we just write that in. So plus 2 times g mu nu, and then we have dx mu by the second derivative of x nu with respect to d tau squared, right? And then times the variation in dx nu. All right, so you can see that this is becoming rather messy, right? And so now we go over on this side and we collect all these pieces, right, with all the indices in the right places. So we collect everything, and we have that, so that's 0, right? 0, which is the variation of the integral between a and b in d tau, right? So that is equal to 3 terms, right? So the first term is this one, and then we have these 2 additional terms. And what we want to do in each case is isolate this variation dx lambda, which is nicely isolated in the first term, and is also nicely isolated in the remaining 2 terms. So we can write this as some sort of gigantic bracket with various things inside. So we still have the 1/2, right? Because the 1/2 was there at the beginning, and in fact it should be here again. So it's 1/2 times the integral from a to b in d tau, and then there is this gigantic curly bracket. So the gigantic curly bracket has the minus g mu nu which is this term here, right? The minus g mu nu, dg mu nu by dx lambda term times dx mu by d tau and dx nu by d tau. So that's the first one. And then it has the remaining two terms, so plus 2 times the derivative with the indices we have there, gamma lambda nu, derivative with respect to x sigma, and then times dx sigma by d tau and dx nu by d tau. Right? So that's this term right here. That's this term right there. Right. And then the third term, so plus 2 g mu nu, or g lambda nu. We want to keep the indices as we have them here. Because we want to factor out a dx lambda, and so we slightly relabel the indices and write this as d lambda nu times the second derivative of x nu with respect to tau squared, and we factor out a dx lambda. Okay. The reason for that is that the indices here are called differently, but we want to group everything together. So we want to call this index lambda. But this index lambda is the mu here, right? So this is going to turn into a g lambda nu instead of g mu nu, right? G lambda nu, and that's what we have here, g lambda nu times dx lambda. All right, so we have achieved what you usually achieve in classical mechanics as well, where you have an integral in dt, and then we have some expression in bracket, and then you have times dq. Right, and then the expression in bracket has to be equal to 0, right? And so now you stare at this expression for a little bit, and you realize that, so what do you realize? Well, you realize a number of things. That first of all, it contains the second derivative of the coordinate with respect to the proper time. Second derivative. And also it contains first derivatives of the metric. First derivatives of the metric. Right? So it contains first derivative of the coordinate and squared, and then it contains also the second derivative of the coordinate, and it contains the derivative of the metric. And this is in fact exactly equal to having the integral from a to b in d tau of the second derivative of the coordinate with respect to tau squared plus the gamma nu mu sigma times dx mu dx sigma by d tau, like this, and then with a g inverse, a metric factored out of the type g lambda nu times dx nu, dx lambda, okay. So let's check everything here. Index nu, mu sigma, index nu is contracted with this, and index lambda is contracted with that. Remember, the metric is symmetric, so g mu nu is equal to g nu mu. And so you get that these two things are identical by using the definition of gamma lambda mu nu, right? Remember, gamma lambda mu nu was written in terms of various derivatives of the metric, and they are precisely the derivatives you have here, because you have a derivative here and you have another derivative here, and they both multiply these velocity terms, right? And so these, right? So those two terms are in fact exactly the same as this one, right? So these two terms are exactly the same as one that contains just a gamma, right? And of course, this term over here is the second derivative one, right? Is that one. So why is it that here we have just two terms that contain a derivative, and in the gamma you actually have three derivatives? Well, because of the symmetry, you have that two contributions from gamma give the same result, which is this one. That's why there is a factor of 2 here, right? So it's exactly the same. And so what does that mean? Well, it means that in order for this variation, right, to be 0, right, and this variation is done for an arbitrary dx lambda. So this dx lambda is arbitrary. This dx lambda is arbitrary, so it can be anything you want. Then for this variation to be 0 for an arbitrary dx lambda, then it means that the expression in parentheses has to be 0. The integrand has to be 0. The integrand has to be 0, right? And so that means that you get, right, from this variational principle, you get the equation of free fall. Right? So let's think about that, because it is really something that is of fundamental importance and interest, right, which in part is at the basis of the geometric interpretation of general relativity. Right? So we have discovered that the equation of free fall is derived, or can be derived, from a variational principle, right, from a variational principle. And that variational principle is that the variation from A to B in d tau is equal to 0, which means that the particle will follow the path of least time, or extreme time. Follows the path of least or extremal proper time. Proper time. Okay, so it means it follows the shortest path. It follows the shortest path in four-dimensional space-time. Shortest or longest path in 4D space-time. Which is a remarkable result. So we have discovered that the equation of free fall is equivalent to the statement that when a particle moves from point A to point B, it does not follow the shortest path. It follows the shortest path in four-dimensional space-time, right? And the shortest path being defined by the one that has the least integrated proper time. So that means that the particle follows a geodesic. Right? It follows a geodesic, but in 4D space, in 3+1 dimensions. Right? The time comes in a crucial way. Right? So now we're familiar, of course, with the concept of geodesics when you talk about the surface of the Earth. Right? Because when you talk about the surface of the Earth, when you have a curved surface, right, North Pole and South Pole, Then, of course, there is a notion of a geodesic there, right, originally introduced already in the 17th century. That is, if you have a point A and a point B here, right, then the geodesic is the shortest path that connects the two, right? And so there's an arc that connects those 2 points. There are many other paths that connect those 2 points, but they're not the shortest one, right? So there's many other paths that will connect point A to point B. But there's only one that is the shortest. There are 2 that are extremal, because of course there's the shortest one, and there's another one which is the longest one, which goes around. Okay, they both satisfy that the variation is equal to 0. So the remarkable thing about this result, right, Einstein's result, is that this equation of free fall, right, which was obtained by just changing coordinate system, in fact has a geometric interpretation. It follows from a variational principle, and that variational principle you might think could be fairly complicated, but in fact it is just about the simplest you can think of, because it says that the shortest proper time is the one that is relevant for the physical path. So that is quite amazing, and so it is a very fundamental result, and because of that I spent the time to actually show you how this variation is done. Because you would think that when you vary an object like this, that you would get something very simple and innocuous, right? That this would be very simple and innocuous, but it is not, because in fact you can see that when you go through the variation, you get all these different terms, and it's actually quite, a little bit more complicated than what it looks at first. And you do get a rather messy expression, and that rather messy expression contains precisely this affine connection, precisely this thing that we had before, and the equation that you get out of it is precisely the equation of free fall. So you have 2 different ways of looking at the same result. One is the kind of dynamical equation of free fall that arises from changes in coordinate systems, right, going from an inertial one to an arbitrary one. And then you have this other point of view, which is geometric. It says, oh, well, I can tell you what path the particle will follow. It will just follow the path that has the least proper time, right? And so it is a remarkable result. And in fact, we can say that this is one of the first, it is one of the first pillars, right, of general relativity. Because if you think about it, we can already see where it is leading us, right? You can see where it is leading us, because we can now visualize what Newton had in mind. Namely, Newton had in mind that you have the sun, right, and you have the earth, and the earth is going around some sort of orbit, right? And the reason why the earth is going around that elliptical orbit around the sun is because there is a force, right? There is a force, and that force is the force that Newton wrote down, right? It involves the 2 masses, the gravitational constant, and 1/r², and it is directed towards the sun, right? So in Newton's picture, right, you have a force, F, that is pulling the earth towards the sun, and of course the sun also gets pulled towards the earth, so it's kind of mutual, right? And if you think about what is coming out of this at this point, is a completely different picture, because the picture that Einstein has is that, well, of course the earth still goes around the sun, right, in an elliptical orbit, right? But there is no mention of force, because we can rephrase what we just learned by saying that the Earth will follow the shortest path in space-time. And so this is Einstein's statement. The Earth follows the shortest path in 4-dimensional space-time. And so how that comes about is because the geometry is curved, and there is a non-trivial consequence to that statement that particle will follow the shortest time in 4-dimensional space-time. So there's a really fundamental difference between the 2 points of view, which I think Einstein started to realize very early on as he was looking at this, that you can really come up with a very different interpretation of the notion of force. Force is replaced, right, or can be replaced at this stage by this geometric point of view. Now, this also has consequences for quantum mechanics. Yes?
Curvature of space is a consequence of the mass or the speed? You gave this example that there's a particle on the end of the disk, and if it's rotated with the
Yes.
speed of around the speed of light, so
Close to the speed of light, yes.
so the speed in the curvature would the space would appear curved.
Space and time would be curved, right?
So is it like due to the speed or maybe due to the presence of masses?
Due to the presence of mass. Mass is the origin of curvature, right? So what we will see, right, we're working ourselves up slowly to construct, like he did, right, to construct the theory and see what it is trying to tell us. And it is interesting that at different stages, it is already telling us something, which is not the complete picture, right? But mass is the origin of curvature. So if there is no mass, then there is no curvature, right? Because then you don't have a gravitational field. If you don't have a gravitational field, right, if there is no acceleration, then the laws are the laws of special relativity, right? And so the metric is then eta alpha beta, and we fall back to what we discussed in the first 3 lectures, right? So it is in the presence of gravity that you do have accelerated frames that look like accelerated frames, right? And you can, in fact, remove those accelerations by a suitable choice of frames. And then you have a curved space, right? Otherwise, the space is flat. So in special relativity, the metric is eta alpha beta. And, well, if, right, in special relativity, the G mu nu becomes an eta alpha beta. And you can see immediately that if that is the case, then, of course, the affine connection is identically 0, right? Because in special relativity, the eta is a constant, right? So when you calculate the derivatives, you get 0, right? All the dg's are 0, gamma is 0, and you fall back to the original equation, which is that the second derivative of the coordinate with respect to proper time is 0, and that's the end of it. That's the end, right? So, but here we're going beyond that, right? So now, as I was saying, this also has some important consequences for quantum mechanics, because Feynman has told us that the amplitude to go from A to B, right, and that is something that, you know, might ring a bell with some of you, but maybe not everybody. The amplitude of going from A to B is proportional to the sum over all paths, which you write in this way, integral over all paths of e to the I over h bar times the action, right? The action, which is the integral with the Lagrangian. Well, in this case, our particle has an action which is in fact the d tau. So this is the integral in d tau from A to B. And this is actually the path integral for a relativistic particle, involves in the exponent just the proper time, right? And of course, the dimensions are not quite right, because what should appear in the exponent is an action, which is you know, usually the Lagrangian times time integral, or in other words, an energy times a time, right? And here we certainly have a time, but we're missing an energy. And so the correct coefficient is, in fact, mc squared, right? Mc squared, and that now has the correct dimensions. And you might think that this has nothing to do with the Lagrangian of classical mechanics, but in fact, it's the same thing. It's the same thing. This is actually the equivalent of classical Lagrangian for a free particle in the relativistic context. So the proper time is a central object when you try to even construct the quantum theory, at least from the point of view of the Feynman path integral. And this is indeed the correct expression for the action, right? So the action is just the proper time, so integrated over whatever distance you're looking at. So anyhow, this is kind of an aside, but it is important because it does generalize to even beyond the classical context. So, well, we have kind of postponed some sort of physical interpretation of our equation for free fall, right? So we have the equation of free fall is again that the second derivative of dx lambda, let's say, with respect to d tau squared plus gamma lambda mu nu dx mu by d tau and dx nu by d tau, that this is equal to 0, right? So this is the equation for free fall, or the equation for the geodesic, right? For the geodesic trajectory. And so x mu of tau is a geodesic, right? And whether you use one name or another depends a little bit on perhaps what aspect of the theory you want to emphasize, because if you refer to it as the equation of free fall, you're still thinking in terms of some sort of forces. If you use the term equation for geodesic, then you're thinking a little bit more in geometric terms, right? Like you have there, right? You have this geometric picture. And of course, the two are completely equivalent because we're talking about exactly the same story. So now, as I said, we have postponed trying to find interpretation for this equation, and so that is what we're going to do next, because at this point, maybe we're talking about something that really has no substance. Because remember, what we have done is just obtain this equation by changing from a freely falling coordinate system, which was denoted by psi alpha, right, to a lab frame, which was denoted by x mu. Lab frame, and this is a freely falling frame, right? So this one's falling down like this, and the other one is looking at this freely falling observer. And so that's how we got this equation, and there wasn't really anything else in it except a change of coordinate. So let's now consider a particle. One particle, right? And let's say that this particle is moving. Well, in order to get something that we eventually might recognize as Newton's equation, we are going to say that it moves slowly, right? So it means all the velocities are small, right? And it is moving in a gravitational field, which we don't want to be the most general one. So in a weak gravitational field, moving slowly in a weak gravitational field. So if we do that, then there's going to be a number of terms that we can neglect, okay? So first of all, the fact that it's slow, right, means that, remember that, of course, dx mu by d tau is just dx by d tau and dt by d tau, right? It's a four vector, dt by d tau. It's a four vector whose entries are those four quantities, right? So if we're saying that a particle is moving slowly, then it means that dx by d tau or dx by dt is small, right? So this part here is going to be 0, slow. So that means that dx by d tau is going to be in magnitude much less than the only other term we have here, for which there is no reason that it should be small, which is the derivative of the time with respect to the proper time. Remember, the time is the time in the laboratory frame. The proper time is always the time it is associated with the freely falling observer. So we have that this one is much smaller than dt by d tau. So that's the requirement that the particle will move slowly, right? And so that allows us to simplify the equation for free fall to the following: dx mu by second derivative of dx mu by d tau squared plus, now this contains indices I, which is 1, 2, and 3, right? And that would be the naught component. So the fact that the velocities are small means that all the I and j components in here are negligible, right? So the I and j components here are going to be negligible, which means that the only one we need to worry about is the naught component. So plus gamma mu naught, right? So that means the ij terms go to 0. So we have the naught component, and the naught component is then multiplied by dx naught by d tau and dx naught by d tau again, right? So dt by d tau, and that is squared, and this is approximately equal to 0 for a particle that is moving slowly. Yes?
Why isn't it slowly being much less than the speed of light? Why is it much less than
No, it is really slow. Really slow, yeah. Yeah, you can include the next order term, right? You can keep it to, we're just interested in the 0th order term, right? The first term which is not 0, right? And so for that, we can actually set the velocity to be very close to 0, and we are still going to get something out of it. Right, so you can just do a Taylor expansion if you want, but that's not necessary in our case. So the second thing we're going to do is weak fields, right? Because we need to know what this gamma is, and the gamma has 3 terms. Well, it has also the inverse of the metric, but then it has 3 derivatives, right? And so that means that we're going to write g alpha beta as eta alpha beta plus h alpha beta. So we're going to set like this. And so this is going to be the flat special relativity type of thing, right? So this is going to be -1, 1, 1, 1, and then 0, right? And h alpha beta is going to be something that is very small, right? And so that's the gravitational field, right, which we assume to be weak. Incidentally, notice that in this case, right, the gravitational field is dimensionless. It's a dimensionless field, right, because it has to have the same dimension as the flat metric, which is, of course, just a matrix of numbers, right? And so, therefore, we now look at what gamma alpha naught is. Right? Now, do remember that gamma, right, in schematic form is 1/2 g to the -1 times dg plus dg minus dg, right? It has these 3 terms, okay? And we're interested again in the leading term in h. So the dg, when you take the derivative of the metric, well, this gives 0 because this is constant, so you get dh. So you get a derivative of h, and so there's going to be 3 derivatives of h here, and that is already of order h, right? And so in the g minus 1, okay, if g is 1 plus h, then 1 over g is 1 minus h. And we already have here terms which are of order h, so we don't need to worry about the terms of order h when you take the inverse of the metric, so we can just use the flat one, right? So this is equal to -1/2. Where is the minus sign coming from? Well, it's the only term that contributes is actually this last one. So it's -1/2 times eta alpha beta. As I said, it's enough to take just the leading term in G inverse. And then the only remaining term is dH naught times dx beta, right? And so all the other terms, they give 0, right? Because we are assuming also that the field, by the way, is static, right? So that the time derivatives of the field are. So the d by dt of the h, they're all 0. We assume that the field is time independent. And so this is the only term that do contribute here is when alpha and beta are some, 1, 2, and 3, right? Because we don't want time-dependent field. And so when beta is equal to I, or 1, 2, and 3, this is just a gradient, It's just a gradient, okay? So it's minus a half times the gradient of h naught naught. Minus a half times the gradient of h naught naught. All right, so assuming that, right, weak gravitational field, everything is time independent as far as the field is concerned. And so we've nailed down what this thing is here, right? Nailed down that. So we can insert that, and notice that the equations of free fall, how many equations are there? Well, clearly there are 4 equations because mu runs from 0 to 3, right? And the 4th equation is not trivial because it involves a relationship between the proper time and the actual lab time. So we're left with 4 equations. Right? And so the 4 equations are the second derivative writing in components, second derivative of x with respect to tau squared, right, is equal to this thing, which was minus a half times the gradient of the h naught naught. So plus 1/2 minus 1/2 times the gradient of h naught naught, right? And then times, we're still left with dt by d tau, so we get to drag that along. And so times dt by d tau, and then squared. And that is equation number 1. Sorry, let me write it like this, which is better. And the second equation is the one that we get when mu is equal to 0. So we get that the second derivative of t with respect to tau squared is equal to what's left over on this side. But gamma naught 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 is equal to 0 because the fields are weak and time independent. So we have that the second derivative of t with respect to tau squared is equal to 0. Okay, so the last equation says that tau, or t, is equal to a plus b times tau. Right? From this equation, there's a linear relationship between the time and the proper time. And so that says that we need to know here what dt by d tau is. So dt by d tau then is equal to just b, right? And that is some constant, right? But the second derivative of x with respect to tau squared is also equal to b squared times the second derivative of x with respect to t squared. Right? So this second derivative here, right, also contains a b squared. Right? And so on this side we have that this thing here is b squared. And that one also contains a b squared, so the b squared cancels out. And so we get that the second derivative of x with respect now to t and not tau, right, is equal to 1/2 times the gradient of h naught naught. And so the dt by d taus have disappeared, and that's all we get. Okay? And so that is very nice because now it starts to become kind of recognizable. It can start to become recognizable because it looks like Newton's equation. So the Newtonian result is that the second derivative of x with respect to t squared, well, that's f equal ma, right? And so that should be equal to minus the gradient of the gravitational field. Remember, the gravitational field, we took the mass out of that, And so normally there would be a mass here in front and would be another mass on this side, but equivalence of gravitational inertial mass makes those two things go away. Right? So normally there would be an m here, and there would be an m there, and the two m's are just deleted. And so with our notation, that is what we should compare, right? And so that, of course, tells us, right, something new and very interesting, and that is that the naught component of the metric. Now remember that the metric was g alpha beta, right, was equal to eta alpha beta plus h alpha beta, where this was considered to be small, right, a small contribution. So when we're talking about h naught naught, we're talking about some piece of the metric, and in particular the naught naught component when the field is weak. And so because of the relative minus sign and because of the 1/2, this tells us that h naught naught is minus 2 times the Newtonian potential plus, of course, possibly a constant, right? Because the constant would drop out when you take the gradient, right? And so now the thing is that you want to consider the case when you go away from whatever the source is for this gravitational field, and when you go far away, the gravitational field should die off, right? So fields die off at infinity. And if the fields die off at infinity, then you would expect that this constant be equal to 0, right? So that would imply that the constant is equal to 0. Why should the constant be equal to 0? Well, because if the constant is equal to 0, then at large distances from whatever the source is for the gravitational field, then the h naught naught will be 0. Is that a good thing or a bad thing? Well, if the h naught naught is 0, far away from any source, then the metric will become the one of special relativity, and that kind of makes sense, right? So when you go away from whatever source of the gravitational field you have, then there is no gravitational field, and you should fall back into special relativity. So that is kind of a boundary condition, right? So the boundary condition is that this constant is equal to 0, right? And so we can translate that back into the g naught naught, right? The g naught naught, remember that this eta matrix, right, as I said a number of times, starts out with -1, and then it's 1 for the rest, right? So the g naught naught, its first component is -1, and then the correction is -2 phi. So we can write this as -1 plus 2 phi. And so that is now a fundamental result, right? It's a fundamental result because what it has allowed us to establish is a connection between the equation of free fall, right, and what appears in it, which is the gamma and therefore the metric, right? We've established a connection between the metric that appears in the equation of free fall and the gravitational field, right? Now we know that that there is this connection, and that connection is incomplete, right? It's incomplete because at that stage we only know what the naught naught component of the gravitational field is supposed to be, and so we have no idea what the Gij are equal to, right? The other components, because there is 10 entries in the metric, right? A symmetric tensor in 4 dimensions has 10 entries, right? And as a result of this kind of calculation, we have pinned down only one of them, which is the g naught naught or the h naught naught. And in fact, we only have pinned it down for the case of weak fields, right? Case of weak fields, right? But nevertheless, so that means that here there is a dot dot dot, right? There is a dot 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 because everywhere we have assumed that the fields are weak, right? And so we have, that's clearly not an exact relationship at this point, but it is one that is quite useful for making some progress in interpreting what is going on. Now, if we do have a point source, right, then we know that phi, right, becomes mg over r. right? Then gravitational potential has this expression. Remember, we take out the mass of the probe, if you want, right? So if you have a point source at the origin, and there is a gravitational field that is coming out of that, and so the strength of the gravitational field is given by the gradient of that thing here. So if we have simply a point source, then G naught naught is equal to minus 1. And now the other thing that we have to be careful about is that there is a minus sign because the gravitational field is attractive. So we get minus 2 mg over r. Right, so if we have a point source, then that is what we get. But the argument, of course, is a little bit more general because in the derivation we didn't say anything specific about the field phi, right? And, well, of course, this now raises some other interesting questions, because one of the interesting questions it raises at this point is that if indeed that is correct, and again, of course, there's going to be plus plus dot dot dot, right? Because we are working in the weak field limit, right? But if we take just what we have, then there is, of course, the possibility that the G naught naught at some point could be equal to 0. It can vanish, right? That suggests the possibility that if you go, right, that if you go to radii or distances which are sufficiently small, then, and they should be comparable to this combination, right, that is twice the mass of the object, say the sun, for example, times Newton's constant, right? And if you go to distances which are comparable to that radius, then the G naught naught, the metric, could vanish. And of course, if the metric vanishes, then we do have strange things happening, right? Because remember that the proper time interval was equal to minus squared, was equal to minus g mu nu times dx mu dx nu. So this could be 0, right? Well, not all of it, but some components are 0, right? And those components determine time intervals because the dx naught is the time, right? And so strange things can happen, and that is precisely what happens for a black hole. Right? Precisely for a black hole, you have this G naught naught that vanishes at the horizon. So we see here already that something interesting could happen. If you go to distances which are small enough. Of course, in Newtonian gravity, there is no 1. Right? In Newtonian gravity, you just have a phi. But here you have this combination. Right? And of course, Feynman speculates in his book about where the 1 is coming from and whether it should really be a 1 or not. Right? And the possibility that actually that 1 arises because you are choosing a specific system of units. You can always rescale the time so that the first term here is 1 as opposed to some other number. And so he goes into a discussion of what eventually must determine the magnitude of the metric, whether it really is sensible to have a metric which goes to the flat one at infinity, right? This is an interesting question because I said in this case that if you go away from any source of the mass, right, like the sun here, right, that if you go at infinity, then you should get back special relativity, right? That you should go into the metric 8 alpha beta, right? And that seems at first a very sensible concept. But in fact, we do know that in the present universe, if you go to very large distances, you get even more mass and not less, right? So whether you should actually get this flat metric at infinity or not is not clear. In fact, we might think that because of the huge amount of the mass distribution that is at infinity from all the galaxies and so forth, that the metric will never go to the flat value, right? Will never go to the flat value, but it will go to some constant that is related to the mass distribution in the universe. And so that raises a number of issues that have to do with the Mach's principle and so forth, which we are going to get back and touch on at some later stage. But here we want to just proceed with what we have. And so one of the things that we can do is at this stage, because we have this very interesting relationship between the metric and the gravitational field, right? Perhaps I should write, again, another thing that we need to remember is that, so the metric is the gravitational field. The metric, we have discovered that the metric, which is, well, something that has to do with, you know, distances, right? It has to do with distances between points in space-time, that is related to the gravitational field, and that the geometry is affected by the magnitude of the gravitational field. So what we can now do is estimate the magnitude of the gravitational field for different size objects. So for example, if we look at the Earth, right, it is very weak. So let's start with something that has a stronger field. So gravitational field at the surface of something that's a little bit more massive than the Earth. And well, it does pay to have also a small radius, right? Because if you have a small radius and a large mass, then you get an intense gravitational field. And the question is, how intense is it? Well, it is 10 to the minus 4. Remember, it's a dimensionless number. It's a dimensionless number, right? The phi. It's clear here, right? Because it's compared to 1, all right? So it's a dimensionless number, and it is 10 to the minus 4 on the surface of a white dwarf. Right, so a white dwarf has a fairly sizable gravitational field on its surface. Not overwhelming, right, because this is still a somewhat smallish number, right? And then if we look at the sun, well, the sun, of course, is just about as massive as a white dwarf, but much bigger, right? So on the surface of the sun, it is about 10 to the minus 6. Surface of the sun. And by the time you get to the surface of the Earth, it's down by another 3 orders of magnitude. Surface of the Earth is 10 to the minus 9. And, well, the next step would be to consider what it is on the surface of something like an atom, right? And a surface of an atom, it is just ridiculously small. It's 10 to the minus 39 on the surface of a proton, right? So if you take r, right, this distance r, to be a Fermi, right, which is 10 to the minus 13 centimeters, then at distances of the order of Fermi, with the relevant mass being the mass of the proton, right, about 1 GeV over c squared, then you get that this field is really very, very tiny, right? So clearly these kind of effects that arise because of general relativity are not going to be that large unless you have huge masses that are involved in it. But we are going to see, I think, in one of the future lectures that these gravitational effects are actually important for GPS systems. And the reason why they're important is even though they're very small, the relativistic corrections, the GPS systems are very sensitive to just tiny relativistic effects and tiny shifts in both the position and the timing and so forth. And so these effects are important at that level, in spite of the fact that the gravitational field on the surface of the Earth is rather tiny, right? I mean, clocks on GPS systems are usually synchronized to times which are the order of nanoseconds or less. And so these effects come into play and are relevant. So now we have about another 3 or 4 minutes, so let me briefly mention time dilation. And we're talking about the kind of time dilation that arises because you have a gravitational field. And so we consider a clock, right? A clock with period delta t, right? And we're going to write that as delta t. And it's some sort of perfect clock. And so that means that delta t is equal to the square root of minus eta alpha beta, and then dxi alpha dxi beta, and then to the 1/2, right? And well, the periods of the clock is going to depend on whether there is a gravitational field or not. So this is now a perfect clock that at first is in no gravitational field. No gravitational field. And in fact, no such clock usually exists, because if you have a clock on Earth, it's going to feel a gravitational field. So this is some ideal clock that we placed, way out away from the solar system in a region where the gravitational fields are completely negligible. And so it's some sort of ideal clock. And eventually, of course, this expression will drop out. We'll get rid of it. And so now we consider a clock in a gravitational field itself. And if it is placed in a gravitational field, if it is placed in a non-zero gravitational field, though, this proper time interval is going to be the same, right? So the delta t is equal to minus g mu nu dx mu dx nu, right? And then to the 1/2. And these two things are going to be the same. These two quantities are be the same because this is basically the proper time interval, and proper time interval is always the same, no matter what observer you have, right? That's already true in special relativity, right? And so now we're going to equate these two to each other, right? And when we equate one to the other, then what we can do is we can take the ratio we can calculate dt by delta t, right? So we take the inverse of this thing, right? So we're going to get 1 over the square root. And so this is going to be minus g mu nu dx mu by dt and dx nu by dt, and then to the minus 1/2, right? So what have we done here? Well, we haven't done anything. We just divided by dt, or if you want, multiplied, right? So this dt goes into the square root, and it appears there, right? And the reason why we do that is because now we can relate dx mu by dt. We can relate that. Well, that is going to be dx by dt and dt by dt, which is, of course, 1. We can relate that to the velocity. So there's going to be a velocity in here, right? And the velocity will appear, but we actually are interested, right? We are interested in clocks that are at rest. So we are interested in a clock that is in a gravitational field, but is not moving, right? So we have the gravitational field of the Earth, for example, right? And we have a clock here, right? We have a clock here, and it is at rest, right? It is at rest in a gravitational field, right? So if it is at rest in a gravitational field, then this velocity here is 0, right? Which means that here there's a whole bunch of terms which are 0, right? Everything that has mu and nu equal I and j, mu and nu equal I and j is going to be 0. So the only thing that really survives, if we are in a gravitational field and the clock is rest, is the g naught naught. And so that means that the only thing that we have is dt by delta t is equal to 1 over the square root of minus g naught naught. Right? How do we get that? Well, it's obvious, right? So mu and nu are equal to 0 because all the velocities are 0. And then we have dx naught by dt. But dx naught by dt is dt by dt, which is 1. So we just have 1. And so this is the time interval attached to this clock in a gravitational field. And this is the proper time interval or proper clock period for a clock that is somewhere out in the middle of nowhere with no gravitational field. Well, who knows what that clock period is, because all we can do on Earth is measure a clock period for a clock that is at some height h1 and a clock that is at some other height, which is h2, right? And both are at rest, right? But where there is some difference in the height. Yeah. Well, we can relate one to the other, and that is going to get rid of the delta t, which is the period of the clock out in the middle of empty space, right, by taking the ratio, right? So we're going to take the ratio. So we have that dt2 divided by delta t is 1 over the square root of minus g naught naught at the point 2. Right. Or we can just write this as dt2 times delta t. Again, let me say that this is the period of the clock out in the middle of nowhere where there is no gravitational field, which we don't know what that period is because we can only do measurements on Earth. But on Earth, we can now have a different point, which is point 1. Right? So this is point 1 and point 2. So at point 1, the clock period is going to be related to the clock period without gravity by 1 over the square root of minus g naught naught of x1 times delta t. And so we're done. We take the ratio. Right? We take the ratio. We take the ratio, and that gets rid of this one. Right? So whatever the period of the clock is in the absence of gravity, that goes away, right? And so now the time interval, the time increment, that is essentially 1 over the frequency, right? If you have a clock that has a given frequency, that is, let's say that they are proportional, right? And so we have that nu2. We obtain that nu2 over nu1. The periods of the two clocks at different gravitational field is just the ratio of g naught naught at x2 divided by the square root of g naught naught at x1, right? And what we can now do is we can write g naught naught, remember, is equal to minus 1 plus 2 phi, right? So g naught naught at 1 is equal to minus 1 plus 2 phi at x1, and similarly for 2, phi of x2. And so we have the square root of 1 plus 2 phi 2 divided by 1 plus 2 phi 1, which we Taylor expand because phi is small. And we just get the ratio of frequencies, right? And it will be convenient to write nu2 over nu1 as this ratio as being 1 plus some small correction, which is delta nu over nu. So we set this as well, and that gives us that delta nu divided by nu is equal to phi of x2 minus phi of x1. And so that is the shift in frequency between the two clocks in a situation where we are precisely, right, as in that picture. So we have x2 and x1, and we measure the period of the clock in the two, and we measure the difference in frequencies between the two. And the frequency difference is going to be related by the difference in intensity of the gravitational field. So the gravitational field is going to get weaker as we go up, right, away from the Earth. And as a result, the clock will actually speed up, right? So the stronger the gravitational field, the more the clocks will slow down, right? So if you have an intense gravitational field, time will go more slowly, right? And how much more slowly is given precisely by this formula, right? That gives a frequency shift. And so we're out of time, and as I said, though, at the beginning, this is of relevance for GPS systems because GPS systems involve a constellation of something like 24 satellites that are constantly going around the Earth, and they have to be perfectly synchronized. And in those satellites, there are both special relativistic effects because they're moving at a certain velocity, which is very small compared to the speed of light, but nevertheless not negligible. So there is a small special relativistic correction due to the motion. But also, they're high up, right? They're something like, 36,000 kilometers up, or actually, I don't think they're just synchronous. They're somewhat lower than that. But the gravitational fields are such that you do get shifts in the frequencies, and you have to account for that when you compare them to a clock on the surface of the Earth. The difference in height makes the clock on the satellite runs a little bit faster because the gravitational field is weaker. So the clocks run faster. And in fact, if you put in the numbers, you find that if you do not account for the general relativistic correction, the GPS systems would be off by 300 miles in a month. The drift. The gravitational redshift effect would cause a drift in the location of GPS systems locations by about 300 kilometers a month, which is huge. They would be completely off. So the general relativistic correction is crucial. You have to take that into account, and it is taken into account, because otherwise the GPS systems would be useless. And it turns out that the special relativistic and the general relativistic corrections are comparable. And of course, the special one has a sign dependence because it depends on which way you're moving. And the general relativistic one has always the same sign because it has to do with the altitude at which the satellite is located. And so anyhow, I think we've covered what I wanted to cover today. And so I'll see you then on next week on Tuesday. We'll continue. Yes?
Is there, like you said, when we go far from gravity, time increases and the
Clocks speed up. Yes.
And when we come close to gravity, it speeds.
Clocks slow down. Yes.
Is there a limit to the slower limit or the fastest limit? Is there any limit?
Well, the faster limit, there is, what happens is when you go away from a gravitational source, eventually the field goes to zero and you fall into special relativity, right? So you go away from the sun and the planets and everything, then you have a limit, and that limit is well defined. When you go towards the source of the gravitational field, then of course the gravitational redshift gets enormous. Right? Because the gravitational redshift involves, at this stage, G0 And what would we notice about G0? We notice that it can actually go to zero. So that means on a surface of a black hole close to the horizon, you can have these redshifts, which are gigantic. And the clocks will slow down. In fact, we can say that the clocks will come to a stop. Right, the time will stop, and so there's all sorts of interesting effects that come out of that.